Topic 13, power of a point. So in previous section, we explored the angles formed by lines that meet inside, outside, or on the circle. So in this topic, we'll explore the length of segments that meet inside or outside a circle. Together, the relationships we will prove and use in this topic are given the lofty name power of a point. So first of all, let's have a look at the meaning of power of a point by looking at this example here. Given chords A, B, and CD that meets at point X, can you prove that XA times XB equals XC times XD? Well, actually, it looks like we need to prove two ratios are equal, right? If two ratios are equal are desired, usually we'll use similar triangles, right? So, for example, we could connect AD and BC. Then, note that angle DAB is inscribed in arc DB. Angle DCB is also inscribed in arc BD, right? Therefore, we have angle DAB equals angle BCD, right? And similarly, this angle here, angle ADC, is inscribed in this arc. Angle CBD is also inscribed in that arc, so we have angle ADC equals angle CBA. Of course, these two angles are vertical angles, so angle AXD equals angle BXC, right? Therefore, we have triangle AXD must be similar to triangle CXB by AA similarity. You can use any two of the three angles, right? And therefore, the corresponding sides are proportional. So we have XA over XC equals XD over XB. So express that in a product format, we have XA times XB equals XC times XD. Did you get it? So, having finished with the points inside the circle, we turn to points outside the circle. So let's consider another question here. Point P is outside a given circle, and A is on circle such that PA is tangent to that circle. C and E are on circle such that secants PC and PE intersect the circle again at point B and D, respectively. Can you prove that PA squared equals PC times PB times PC also equals PD times PE? So here we can start as we did in previous problem, drawing AB and AC to make triangles, right? Since angle ACB equals half of AB and angle PAB equals half of arc AB, we have triangle PAB must be similar to triangle PCA by AA similarity, right? Therefore, we have PA over PB equals PC over PA. Of course, that gives us PA squared equals PB times PC, right? Just as there was nothing special about the course we looked at in the previous problems, there's nothing special about the second PC here. By exactly the same reasoning, we can have PD times PE also equals PA squared, right? So we have PB times PC equals PD times PE as well. Notice that Once again, there's nothing special about the tangent and the secants we have chosen except that they have the point P in common. So we can put the facts we have proved in the last two problems together, this problem and this problem, in a single statement. So let's have a look at this property here. Suppose a line through a point P intersects the circle in 2 points. Pardon. Sorry. The power of a point theorem states that for all such lines, the product PU/PV is constant. We call this product the power of point P. For example, in the figure at right, applying power of a point to x with respect to the circle shown gives us xa times xb equals xc times xd. In the figure at left, the power of a point P with respect to the circle gives us PA squared equals PB times PC, which also equals PD times PE. We think of a power point whenever we have a problem involving intersecting segments and a circle. So I'll give you 1 minute to have a look at the property here, and we'll be using that to solve some example problems below. Okay, next let's consider a quick quiz. Course Ty and OP meet at a point K such that Tk equals 2, Ky equals 16, Kp equals 2 times Ko. Can you find OP? Okay, first let's do a quick sketch to illustrate the situation here. So we have a chord Ty, another chord OP. They meet at some point K. So from the power of a point K, we have Kp times Ko equals Kt times Ky, right? Substituting the given information in this equation yields 2 times Ko times Ko equals 2 times 16, from which we find Ko equals 4, right? Therefore, we have Kp equals 2 times Ko, which equals 8. And so OP equals Ko plus Kp equals 12, right? Any questions? Okay, good. If no questions, let's consider another one. In the diagram, CB equals 9, BA equals 11, CE equals 18. Can you find the length of DE? Again, I'll give you 30 seconds to consider this problem, and after that, we'll have a look at the solution together. Alright, have you finished? Let's have a look at the solution together. So we have two intersecting secants. So we apply power of a point, which gives us CD times CE equals CB times CA, right? Therefore, we have CD times 18 equals 9 times 20. Therefore, we have CD equals 10 and DE equals CE minus CD, which equals 8. Any questions? Okay, great. No questions. Let's have a look at another one. Points R and M trisect PS, so PR equals RM equals MS. Point U is the midpoint of PQ. TM equals 2, MQ equals 8. Can you find the length of PU? Okay, again, very straightforward question, right? Circles, chord length, and secant length. This is a typical job for power of a point theorem. The power of point M gives us mr times ms equals mt times mq, right? We know that rm equals ms, so substitution gives us mr squared equals 2 by 8, and therefore we have mr must equal 4, right? And therefore PR equals MR equals 4, and PS equals 3 times MR, which gives us 12. Since U is the midpoint of PQ, we have PQ equals 2 times PU. Now we can apply the power of point P to find PU times PQ equals PR times PS. Again, substitution gives us PU times 2PU equals 4 by 12. And this actually solves PU equals 2 square root 6, right? Any questions? Okay, good. If not, let's have a look at some more power of a point problems. So consider this problem here. These on circle O and secant XZ hit the circle at Y such that XY equals 6, YZ equals 5. Given that X is 9 units from the center of this circle, can you find the area of that circle? Again, I'll give you 1 minute to consider this problem, and after that, we'll have a look at the solution together. Okay, let's have a look at the solution together. We start with a diagram. This is our circle O, some point X is here, right? XZ is a secant line. Hit the circle at Y. Sorry. Y should be here. Because XY, okay, it's given that XY equals 6 and Y is equals 5. Given that X is 9 units away from the center, okay, that means we can continue segment XO to hit the circle again at some point V, and let's call this point is W. So we can use the power of point X. We have XW times XV equals XY times XZ. If you let the radius of the circle be R, substitution gives us XO minus R times XO plus R equals 6 times 6 plus 5, right? And XO equals 9. Then we have 9 minus R times 9 plus R equals 66. And therefore we can solve R squared equals 15, right? So the area of the circle O is given by pi R squared. This gives us 15 pi, right? Did you get it? Any questions? Alright, great. If no questions, let's consider another quick quiz. So as shown here in this diagram, can you find the length of BF and can you find the length of ED? Alright, have we finished? Okay, first question A, we can find BF with power of a point. FE times FB equals FA times FD, right? And therefore we have FB equals FA times FD over FE. And this gives us 20 over 3. For the second question, well, PowerPoint won't get us anywhere with ED. Our proof of PowerPoint guides us to the answer. Specifically, since we have angle FDE equals angle FBA, and we also have angle AFB equals angle EFD, right? We have triangle AFB is similar to triangle EFD. And therefore we have ED over BA equals EF over AF. Hence EB equals EF times BA over AF, right? So that gives us 18. Any questions? Alright, good. If no questions, let's consider another one. Given that segment YD bisects angle XYZ in the diagram, right? Prove that XA equals ZB. So I'll give you 1 minute to consider this problem and then I'll have a look at the solution together, okay? Alright, let's have a look at the solution together. So this problem involves lengths and angle bisector, chords, seconds, and circles. Therefore, we should consider the angle bisector theorem and power of a point theorem. The angle bisector theorem applied to angle bisector YD of triangle XYZ gives us XD over XY should equal ZD over ZY, right? This is by angle bisector theorem. However, we need something with XA and ZB. Therefore, we turn to the powers of points X and Z, which respectively gives us XA times XY equals XD times XZ and ZD times ZX equals ZB times ZY, right? Seeing some common terms in these two, along with terms from our angle bisector theorem equation, we know we are on the right track. So we solve these two equations for XA and ZB, and then we have XA equals XD times XZ over XY, and ZB equals ZD times ZX over ZY. We need only show these two expressions are equal. We have XZ in common, and we already know XD over XY equals ZD over ZY here from our angle bisector theorem. So we can put this together to show XA equals XD times XZ over XY, which equals XZ times XD over XY, and ZB equals ZD times ZX over ZY, which gives us XZ times ZD over ZY, right? So these two ratios are equal, XY equals XY, and therefore XA equals ZB. This is how we can prove these two lengths are equal. Okay, any questions? Okay, good. If no questions, let's see another one. Point O is the center of that circle. AB is perpendicular to BC. AP equals AD, and segment AB has length twice the radius of the circle. Can you prove that AP squared equals PB times AB? Alright, let's have a look at the solution together. Since diameter BC is perpendicular to AB at point B on the circle, AB must be tangent to that circle, right? Therefore, the power of point A gives us AB squared must equal AD times AE, right? We are given AB equals twice the radius of the circle of which DE is a diameter. So we have AB equals DE. Since we are also given AD equals AP, so we have AB squared equals AD times AE, which is AD times AD plus DE, which equals AP times AP plus DE, which equals AP times AP plus AB, right? Expanding and rearranging, AB squared equals AP times AP plus AB gives us AB squared minus AP times AB equals AP squared. So you can actually factor that to AB times AB minus AP equals AP squared. So because we have AB minus AP equals PB, then we have the desired expression PB times AB equals AP squared, right? Any questions? Okay, because of the time constraints, I'll leave the last question for you to solve after this class, okay? You can consider this as one of your homework questions. Alright, if you don't have any questions, I'll see you next time. Bye.